The second exercise of this series deals with recursive aggregation. So this is going to include an introduction to recursion, which is a type of nesting of functions, which we'll get into once we open up Grasshopper and look into the Python script editor. First, though, I just want to explain the logic of aggregation in Rhino so that we can kind of look at it, understand it, unpack it, and then move into Python and try and recreate the manual moves that we made in Rhino with the Python script. The first thing that we want to do is we're going to just draw a line. It doesn't matter where this is or how long it is, but we just need to draw one line. And then I'm going to type rotate, select that object, make sure copy is on, click at one endpoint, the other, and then type 60. So this gives us a rotation of that line, rotated at 60 degrees, and we're going to just select that line we just made, click one endpoint, and rotate it to make a triangle. So now that we have this triangle, we can type join to join it, select the entire curve, hit Alt and left click, and drag up. Now that we have that, we can draw surfaces on this to connect each of the points in these two triangles. So we can do that by typing srf p, just surface point, and then clicking on each point that we wish to draw surfaces on. We can see that the inside face here is green and the outside is gray. So that's signaling that there is a back face and a front face. We want all of our front faces to be on the outside. So you can achieve this by just constructing the surfaces in a counterclockwise direction. For the faces with only 3 points, instead of drawing another point there, we can just hit enter and it will finish with only 3 points in the face. Now that we have all of these surfaces made, we can type join to join them all together. So the idea of aggregation, which we can maybe look at this example one first, is to take an object and reorient it relative to itself, copying that object each time, so we can continue to kind of iterate these transformations. One way to replicate this manually is typing orient 3 point, and we can select here at the bottom point 0 as it's labeled, point 1, and then point 2. And then if we want this to grow downward, what we want to do is just click on those same points in reverse order. So point 3, 2, 1. Now we can keep this kind of pattern going and continually grow downward, or we can change it the next time, aggregating on another side, always just reversing these source points in order to get to target points. Now we don't have to do that. We could orient this triangular face to the quadrilateral faces, but it doesn't always guarantee a clean operation moving forward in the aggregation. And we're going to open up Grasshopper and set this up inside of Grasshopper in the Python script editor. So you can open up the reference file Python intro-exercises01, and there is the recursive aggregates component already made. If you don't have this, just double click into the canvas and type GhPython script. And to get it to look like this one, just right click on Python, type recursive aggregation or aggregates. And then we're going to right click on this X, hit capital B at the top, capital I instead of that Y. And then we can right click on the I, go to type hint integer. And then one last thing is we're just going to remove that out and make the output parameter a capital A. So I already have this. I'm going to just use this one, but I'm going to walk through the setup of this script. So to give a quick preview of what these scripts can do, I have a slider here which sets the maximum number of iterations. So if we just slide this, we can see that not only is it growing and aggregating, but it's also branching occasionally. And it quickly becomes far more complex than we can do manually inside of Rhino. These are relatively simple rules, so if you spend time designing a nice object that can aggregate well and rules that avoid self-intersections and have nice branching patterns, you can end up with really nicely complex outputs with relatively straightforward inputs. First, we're going to just talk about recursion as a principle. So the idea of recursion is basically that we can feed items into a function, and then inside of that function, call that function itself under some conditions so that it doesn't just run forever. So we can continually perform the same or a similar transformation throughout time. So a simple example of this might be, I'll just re-import this library, so import Rhino script as others. Okay, those three libraries, and then just to make sure we want to operate inside of the Rhino document right now, so I'm going to say sc.doc equals rhino.doc. And now I'm going to make a point. rs.addPoint, and we can make a point 0, 0, 0. If we hit test, we see a point is made at the origin. So if we wanted to move this point one step to the right in the x direction, we may say point equals that point that we made, and we can say point 2 equals rs.object point, and then it requires a translation input. So this translation input is a vector. So we could just say 1, 0, 0. This is going to move it 1 unit in the x direction. We could also create a vector first by saying vec and setting vec equal to a vector. And this is going to take 3 numbers. So same thing, 1, 0, 0. And then we can store or use vec in our move object function and hit test. So we could see that it quickly made a point at the origin and then moved it 1 unit to its right. Now, if we didn't want to do this transformation once, but instead we wanted to do it 10 times, there are a couple ways we could do it. We could loop through moving it once each time. So that might look like 10, and then just tab those in. So vec is going to equal that same vec. In this case, we actually don't even need that in the loop. We can just use point 2 and that move function in the loop. And when we hit it, we can see that the point zooms off in the x-axis. Another way to do this, though, instead of just looping through, would be to use recursion. So for recursion, we first need to establish a function. So def, and then we can just call this move. And then we're going to just move this move object inside of the doMove function. So in this case, doMove takes no inputs, but when we hit test, it's not actually running this move object anymore. But before we call this function, we need to input parameters specified above. So we need to input the original point, and then we need to input the vector translation. We also need to add these in our function definition. So we can say point and then vec. So we can now see that it's doing the move 1 time, moving that point once to its right. If we wanted to do this multiple times, what we could do is say inside of the function do move, this time using the point we just moved and still using that original vector. Now we can't hit test here because it would just run forever calling the function over and over and over again. So what is important is that we program in conditionals that allow it to stop at a certain point. So if we type functions equals 0, and then we say iteration equals 1 at the top of the function. You can do it at the top of the function or in this conditional down here before we call the recursion. But I like to do it at the top. That way I always just remember it, even if this condition is not true. So the next step is to make a condition. So if iterations is less than, and then some number, so let's say 10, then call do move point to vec. So now we should see it calling this function once, and then once it calls it, it will recursively run for 10 steps. So we're getting an error here because I did not feed in iterations into the recursive function. So it's important that we actually feed it into the function. That way it can update and be read to both add and then use in the conditional statement. So now when we hit test, we can see that it's running for 10 steps. If we wanted to change this conditional to 30, we can see it run for 30 and then stop. So that is a basic introduction to recursion. It's just the idea of nesting functions within themselves and then creating some kind of iteration conditional and calling it outside to initiate the recursion. Now, what we want to do is use this method of recursion to aggregate the objects like we did manually. So if you're just using this base file, then this brep is already set here and is labeled as B, and then we have our iterations input as I. So like we did manually, what we want to do is break down this brep into each of its surfaces and find each of the corner points so that we can use those to orient based on 3 points. And then we're going to recursively do this orientation. We are going to start by making a function. So this function is going to be called aggregation. So once we've defined the function, we're going to call the function. Then we want to pass in certain variables. So we're going to pass in I, label it here, iterations inside of the recursion, inside of the function, and we're going to pass in rep. So when we call this, I'm going to use the parameters that are input inside of Grasshopper to satisfy those 2 parameters of the function. So in this case, actually, we're going to use 0 as the input to the iterations, and then we're going to use the I as a value for the maximum number of iterations to be used later. So the first thing we want to do is explode each of the surfaces into individual surfaces. So we can do this by typing surfaces equals rs, and then we're going to use the command explode polysurfaces. And then we're going to input here the object IDs, which were those numbers that popped up. So brep, and then hit enter and print surfaces. So if you get this error unable to convert the GUID into a brep, this is because I left the sc.doc equal to the Rhino active doc. We actually want to change this to the gh doc So reset the script context document to the GH document instead of the Rhino one. So if we hit test again, we can now see that it's printing out the surfaces here. So each one of these is the GUID for a surface in this poly surface. We can extract the corner points by looping through each surface and extracting its corner points. So for surface srf, colon, enter, and now we're tabbed in here. We can say points equals rs dot surface and then points. And we can see here it returns a list of the control points. So that's perfect, that's what we need. And then if we hit enter, print points, we should see it outputting the corner points of each of these surfaces. As a personal preference, I like to just place this list of points back in a kind of master list of points. So I'm just going to hit enter and make a list of above on line 68 here, surface points. I'm just going to make that a blank list. After the points in line 71, we can now append two surface points. So surface points dot append, and then add those points to that surface points list. So when we print surface points, we now see a list of these lists of points. So a nested list. Now what we want to do is we want to orient and copy the object. So we can type rs dot orient object and open parentheses. And we can see that the parameter inputs here are an object ID, a reference, and a target. And then it should say orients a single object based on input points. If two 3D points are specified, then it will be similar to Rhino's orient command. If more than two 3D points are specified, then it will operate like orient 3 point, similar to what we did manually. Okay, so we have a reference geometry that would be our vref, and then we are going to need reference points and target points. Right now, those reference and target points are not defined, but we can go ahead and specify those by saying reference equals, and we're going to just use our surface points list. So let's say surface points, and then we can use the first surface faces set of corner points. So right now, all we would be doing is orienting an object from 3 points to the same 3 points, which means it's not going to move at all. It's just going to move the object into its same position and stop. If we want to visualize what this is doing, we can just at the top here say equals, and we're going to just make this a blank list because later on we're going to add multiple items to this, so we can just leave that blank. And for now we are going to say a dot end. That item is not moving, so we still have that same object there. So one potential option for this is similar to how we did it manually, where we actually specify that we want a set of points equal to the corner points on one particular face. We only care about the first 3 points. So we can actually specify not just the points on this surface, but just the first 3 by opening another brackets, and we're accessing inside of the list, inside of the first item. So this is accessing index 0 of the outer list, and then we're going to access additional indices in the inner list, in the nested list. So to specify a range of indexes that we want to access, we can type any value, so 0 in this case, and then colon, And we want 0, 1, and 2. So we're going to say 0 up to 3, and then close the brackets. Now, when we print these points, we can see that we have 1, 2, 3 points printing. So that's what we want. That's looking like the setup is working. So now we can set our reference points equal to points. And if we want to be more specific about this or visualize this a bit more clearly, we can set this to points 0, points 1, points 2, and set all of that inside of a list. Similar to when we did it manually inside of Rhino, we want to just take this list, and instead of, let's say this is clockwise, instead of counting this clockwise, we just want to count counterclockwise. So we can do this by going, instead of 0, 1, 2, 0, 2, and then 1. So now it has reoriented that piece, but it's only doing that one time. So what we want to do is actually call the recursion here and set this new object and feed this new generated or oriented object into the recursive function so that it can step through this reorientation or aggregation. So I'm going to delete this append for now, and we can set up our recursion. So this newly oriented object, we're actually going to say new brep equals, and then we also need to a copy of this object so that we're not just moving it in space, but we're also copying it and storing all of the items. Now, to make sure we are storing all of the items, what we can do is at the top, do the list A that we were just using for visualization in Grasshopper. And that way, each of our breps that come into the aggregation function are going to append to that list so we can later use them. Now, it's copying, but it's not actually calling this function recursively. So in order to do that, we need to say if iterations is less than I. So in this case, we're feeding in 0 as the first input to the iterations. And then after that, we're going to need to count up. So right under this append or even above it, you can say iterations plus equals 1. This way we make sure that we are not calling the function recursively forever. So once the iterations gets above I, it will stop. And now we're going to call aggregation, input iterations, and then not brep, but instead new brep. This will not only reorient the object, but then it will continue to reorient on the reoriented object. So now if we hit test, we can see it's basically just reorienting back and forth several times. So if we look here, we can see that it is doing it 12 steps, outputting 12 breps, but they're just happening over top of one another. So one way to fix this is actually to set up conditional statements so that each time the aggregation changes which surface it is reorienting on. So we can say if, and then we can use the iterations count as a way of following this rule. So if, and then we're going to use a symbol called modulo, which is the percentage sign. And let's say modulo 3 equals 0. We can tab all of this in. So right now, what this is telling us is that if iterations modulo 3, so if the iterations value divided by 3 results in a remainder of 0, then run everything inside of this. So if we run this, we're going to get an error. This is because we won't be running this until iterations equals 3. So we won't have defined the points reference or target. So what we need to do is make an else statement. And then what we can do here is just change this to a different surface. So I just selected index 2. Now if we hit test, I think eventually it is falling back on itself. So maybe let's try 3. Okay, it still seems to be. And if we change the modulo to 2, it gets very messy. So another way to fix this is to add an elif, so that we can actually get 3 different rules running, and we can try to balance each of these rules. So we can try elif iterations modulo, and then you just want to make sure it is not a multiple of this, otherwise it may not do very much. So let's say if this one is iterations 3, then this can be 5. So now our aggregation is looking a little bit better, and it's actually following a relatively periodic pattern, not self-intersecting. So the next question here is, if we wanted it to not just be one aggregation, one continuous line of transformations, but we actually wanted this thing to branch, how might we do this? So if you think about the kind of logic with recursion, we're feeding in one object, and then we're calling the function inside of itself and feeding in the transformed version of that object back into the function, and then transforming it again. So if we wanted to create a branch in this, we can use our structure of our conditionals, and we can add a second object. So in this case, I'm going to use a different surface, and we can say ref2 target 2 points 2, so that those don't get confused with our other sets. And then we want to make sure that points 2 is set in each of these. Okay, so now we have an additional set of references and targets, but we only want to branch for the 5th step in the iterations. So this means we're going to want to copy this line here, actually do it inside of the elif statement in this case. So instead of new brep, we can say branch brep. We're still going to keep this the same, but instead of ref and target, we can use ref2 and target2. So we've now made a new geometry. So we have 2 geometries, but if we hit test right now, it doesn't really look like it's doing much. So it still kind of looks the same. You can see that it's doing something strange there, but it's not really doing much. It still looks like it's a single aggregation line. So this is because we need to call this function 2 times inside of this function. So we're going to move this and say, if iterations is less than I, pass in iteration still, but instead of new brep, we can pass in the branch brep. So this is going to create a series of branches. So when we hit test, we can see now that it's branching, and I think quickly it will become self-intersecting, but it is doing the branching. The last exercise for this series is going to cover controlling Rhino inside of Python. So this is going to be mainly to transition our thinking from scripting as just making geometry or editing geometry attributes, and to also start thinking about ways in which we can document the process of making that geometry. So how are we engaging with the Rhino interface and documenting the process of our programming, maybe through animations or changing our views recursively as we kind of build. So in this example, we're going to map a camera to a particular path and allow that camera to change its location and target view according to the aggregation output. So we already went through aggregation, and if you use your output from that base file, that will be enough for now. So we're going to just start with that, and we can make a new GhPython script component. We can label it camera follow, and then add 2 input parameters, 1 index, which we will connect this iteration slider to, and the other is curve. So this curve is going to be our camera path. We can also just name this path or camera path. That may be more appropriate. But what this component is going to do is actually take the viewport information and allow us to make an animated camera motion path. So in order to set the camera, we're just going to need a curve input. So I've just drawn a random curve inside of Rhino. You can draw anything you like. I would experiment with 3-dimensionalizing it a bit, so seeing what kind of paths or angles around the object you can do. And for now, I'm just going to use a static target, but you can also a camera location and a camera target path. So it could follow both if you wanted to do that. So I'm going to just go ahead and open up this GhPython script. We have the example in there. I'm going to comment that out and start from scratch. So the first thing to do is always import our libraries. So import Rhino script and script context. Then we want to make sure that we are setting our sc.doc equal to ghdoc. A couple things are important here. So first, we don't need the curve as an input, but instead we need points along the curve, because we're going to feed each one of those points in as potential camera locations. What we can do is set points equal to rs.divide curve, and then this divide curve takes input parameters of a curve ID and segments, so a number of segments. Input curve is going to be the curve from the path input from Grasshopper, and then we can create number n or keep it as divisions. Then we just need to make variable divisions and set that equal to a number, so 60. So now if we print points, it's going to be 60 points along our input curve path. In order to update the camera inside of Rhino, we need a camera location and a camera target. So first we're going to set location. The location is going to be the point on this curve based on the iterations counter in that slider in Grasshopper. So what we can do is use the points, and then we're going to use the index as an index for the location. And for the target, we can just create a point. The next step is to create a variable VP, which we can set to the c.doc view.active viewport. So we're setting this as the viewport object. This way we can call VP or If we wanted to, we could write all of this out again, but it's much easier to just type VP dot, and then we're going to set camera location. And right now it's not outputting, so if we did want to see what parameters this actually requires, we can say period and then set camera first location, and it is going to take a point 3D. So set camera location point 3D, we're going to use loc. And then it is also going to take an input parameter for update target location, which is false because we do not want to update the target location with the camera location. Next, we're going to update the camera direction, so set. Again, if we want to see the parameters, we can just copy sc.doc and set camera direction, open parentheses. So this is going to take a camera direction vector 3D and update target location boolean. So in this case, we do want to update the target location, and the vector 3D is not going to be the target, but the target point minus the location, which will give us the vector from the camera location to the target, which is the origin. So now if we hit test, so it should be ready to go, and as we slide through this slider, we can see that the recursion is both iterating and the camera location is following the curved path. If we wanted to make this visual a bit more professional, there are a few display options inside of Grasshopper. So the first thing I'm going to do is change the Rhino viewport display mode to Arctic. So click on that drop down and go to Arctic. It still has this kind of wireframe or ghosted view from the Grasshopper display. So I'm going to just highlight over all of those components, click the scroll wheel and click the blindfold. That's going to hide the display. And what we want to do is create a custom preview of these recursive objects. So double click, hit custom, and then preview, go up to the custom preview component, and then plug this A output from the recursion into the custom preview output. If we had particular objects, so let's say this object, we had a material on it, so we can go to the materials tab, go to the little tube of toothpaste, and then click on the layer, use new material, and we could say plastic. So we now have this new plastic material. We can make it orange plastic, and we can also adjust the Rhino environment by going to Render Tools, toggle Environments panel, click the plus icon, and then import from Environments library. And we could change any of these. You can kind of experiment with these in your own time, but we could use maybe Warehouse. And this will give us an HDRI environment inside of Rhino. If we double click on that, it will set to our active environment. So that's currently our active environment. And now if we right click inside of Grasshopper on the M for the custom preview, we can actually set that plastic as our preview material. So we can hide those again. And now as we scroll through this, we can see that our object previews are using that custom material from Rhino and updating with the environment lighting. If you wanted to export this animation, right click on the slider and select Animate, and then we're going to go to Browse. Then we can make a Frames folder, hit OK, So once you've selected your folder, create a new folder called frames, and then we can name this whatever we would like. So in this case, this is going to iterate through a series of numbers, so giving us 0, 0, 0, whatever that value may be. It's going to be a .bmp file. I sometimes have issues if I change the extension, so I would just leave it and deal with it in Adobe Premiere later. And then a couple other options are which viewport, so perspective viewport is what we're going to use, and then the resolution, that looks fine, and then the frame count. Since there's only 60 that we're stepping through, we can just keep it at 60 and then hit OK. This is going to step through and save out our frames, and we can see them being saved in our frames folder in the folder we selected on our desktop. Later, we will be able to bring this into Adobe Premiere and make an animation straight from our recursive growth function. So we can see it output all of the frames, and you get a relatively high quality animation for a pretty quick process. Okay, that is all for these exercises. Try to combine both of these, so the looping exercise on colored point arrays and this recursive aggregates. Try to find creative solutions for how you might use these. So is it branching more times, or finding different rule sets for the branching, using mathematical functions to control the conditional statements, adding color to the aggregation? Any of these things are exciting ways to merge both of these simple design exercises, but being creative will help you to more quickly learn Python and get into its interface. In the next tutorial set, we're going to be dealing with classes.